Opening. A word enters the observatory. A word enters the observatory. It is not a letter, not a symbol, but a unit of meaning, a fragment of language, a point in an unseen lattice. It moves through the machine with quiet precision, its shape undefined, its purpose clear. The observatory is a place of quiet calculation, where data is not merely stored but transformed, where meaning is not spoken but measured. The word arrives as a vector, a point in a space where others wait in silent expectation. It is not the first, nor the last, but one among many, each carrying its own weight in the silent architecture of understanding. Numbers in this place are not the essence of meaning, but the tools by which it is approximated. They are the learned representations, the coordinates that allow the machine to navigate the vast terrain of language. These numbers do not define the word itself, nor do they capture its inner meaning. They are the result of patterns, of repeated associations, of the way words appear together in the world. They are the echoes of usage, the remnants of context, the silent agreements of a language in motion. In 2013, Mikolov et al. Proposed a method that would change the way words were understood. They introduced the continuous bag of words, CBOW, and skipgram architectures, which allowed for the creation of word vectors that could capture semantic relationships. These models were not concerned with the internal meaning of words, but with how they related to one another. A word's vector was not a definition, but a reflection of its role in the language. It was a point in a space where other words hovered, each with its own position, each with its own distance. By 2014, Pennington, Sacher, and Manning refined this approach with GLO-V, a method that used global word-word co-occurrence statistics to train word vectors. Unlike the earlier models, which relied on local context, GLO-V drew from the broader patterns of language. It was a bridge between the statistical and the semantic, a way to capture meaning through frequency and distribution. The vectors it produced were not arbitrary, but grounded in the way words appeared together in text, in the way they formed the fabric of communication. Then came BERT in 2018, a model that would push the boundaries further still. Devlin and his colleagues introduced a method that learned deep bidirectional contextual representations, allowing words to be understood in the context of both their left and right neighbors. This was a shift from static representations to dynamic ones, from isolated points to interconnected paths. Words were no longer fixed in meaning. They became fluid, shaped by the sentences they inhabited. In 2019, Reimers and Gurevich extended this idea with Sentence-BERT, a model that used Siamese and triplet structures to create sentence embeddings. It was not just about individual words, but about how they combined to form meaning. Sentences were treated as units, and their representations were compared using cosine similarity, allowing for a more nuanced understanding of language at the sentence level. This was a step toward capturing not just the meaning of words, but the meaning of entire phrases and ideas. Each of these methods, though distinct, shares a common thread: the pursuit of meaning through pattern. They are not the only methods in use today, nor are they the final word on the subject. Language is vast, and the models that attempt to represent it are only one part of a larger, ever-evolving landscape. They are tools, not truths, and their purpose is not to define meaning, but to approximate it. The word continues its journey through the observatory, moving along a path that connects it to others, shaping and being shaped in turn. It is not alone, but it is not yet complete. In the quiet of the machine, it waits, a point in a space of many, a word in a world of words. Chapter 1. The Vocabulary Table. In the quiet of the observatory, where the hum of distant machinery blends with the soft sigh of the night, the mind traces paths through the vast expanse of language. Words, once mere symbols, now take shape as points in an abstract space, each carrying the weight of meaning, context, and history. Here, the study of language is not about the sounds or shapes of letters, but about the relationships between them, how they connect, how they diverge, and how they are mapped into the machine's mind. At the heart of this mapping lies the vocabulary table, a foundational structure that transforms words into numerical representations. Each word in a corpus is assigned a unique identifier, a vocabulary ID, which serves as a reference point in the model's internal space. These IDs, though arbitrary in their numerical assignment, are not meaningless. They are the first step in converting language into a form that can be processed by algorithms, a bridge between the symbolic and the mathematical. To represent these IDs, models often use one-hot vectors, arrays of zeros and a single one, where the position of the one corresponds to the ID. This method is straightforward, yet it introduces a limitation. The one-hot vector does not capture any notion of similarity between words. Two words, even if semantically related, will have no overlap in their vectors. This is why the vocabulary table, while essential, is not enough on its own. It is a starting point, a way to index the words, but it does not encode the relationships that make language meaningful. The next step in the transformation is the lookup table, a dense matrix that maps each vocabulary ID to a vector of a specified dimensionality. This vector, often of size 300 or 500, becomes the word's representation in the model. The dimensionality is a crucial parameter, determining how much information can be encoded and how the model can generalize across words. It is not a direct reflection of the word's meaning, but a space where meaning is approximated through patterns and co-occurrence. The work of Mikolov et al. In 2013 marked a turning point in this endeavor. Their CBOW and skip-gram models introduced a way to learn continuous word vectors by leveraging the statistical relationships between words in a corpus. These models, trained on large text data, captured semantic and syntactic regularities, allowing words to be represented in a way that preserved their relationships. The vectors learned by these models were not just arbitrary. They were the result of millions of co-occurrence patterns, shaped by the structure of language itself. In 2014, Pennington, Sacher, and Manning introduced GLO-V, a method that built on these ideas by using global word-word co-occurrence statistics. Rather than relying solely on local context, GLO-V incorporated global statistics to create word vectors that reflected both semantic and syntactic similarities. This approach provided a more nuanced representation, capturing the broader patterns that underlie language. The evolution continued with BERT, developed by Devlin et al. In 2018. BERT introduced a new level of sophistication by learning deep bidirectional contextual representations. Unlike previous models, which treated words in isolation, BERT considered both left and right context, allowing for more accurate and context-sensitive word representations. This shift from static to contextual embeddings marked a significant leap in the field. Building on this, Reimers and Gurevich introduced Sentence-BERT in 2019, which extended the concept of embeddings to entire sentences. By using Siamese or triplet structures, Sentence-BERT enabled the comparison of sentences through cosine similarity, opening new possibilities for tasks like semantic similarity and natural language inference. Each of these methods, while distinct, contributes to a broader understanding of how language can be represented and processed. They are not the only current methods, but they are influential, shaping the landscape of natural language processing. The vocabulary table, with its vocabulary IDs and one-hot vectors, is the foundation upon which these models are built. It is a silent, unchanging structure, yet it is the first step in a journey that leads through the vast and intricate space of language. Chapter 2: Meaning from Neighbors. In the dim observatory, where the air hums with the quiet rhythm of data, meaning is not found in words alone but in the spaces between them, the paths they trace, and the neighbors they surround. The idea that meaning is derived from context is as old as language itself, yet it has only recently been given shape through the lens of computational linguistics. At its core, this approach rests on a simple but profound principle: words do not exist in isolation. They are surrounded by other words, and it is through these relationships that their meaning is revealed. This concept, known as distributional semantics, suggests that the meaning of a word is reflected in the company it keeps. If two words frequently appear in similar contexts, they are likely to share meaning. This was the foundation upon which Word2Vec was built, a model introduced by Mikolov et al. In 2013. Word2Vec, through its two primary architectures, continuous bag of words, CBOW and skip-gram, offers a way to transform words into dense vectors that capture these relational patterns. CBOW predicts a target word from its surrounding context, while skip-gram does the reverse, predicting context from a target word. Both methods rely on the assumption that words with similar meanings will appear in similar contexts, and through their training, they learn to represent words in a way that reflects these relationships. The power of these models lies in their ability to capture not just the meaning of words, but also their usage patterns. Words that appear in similar contexts tend to share semantic properties, and this is precisely what the model learns. The vectors produced by Word2Vec are not static. They are dynamic representations that encode the nuances of language. For instance, the word king might be positioned near queen, royal, and crown, reflecting its semantic associations. These vectors are not arbitrary, but emerge from the statistical patterns. In the text they are trained on. The idea of using context to derive meaning has since evolved. In 2014, Pennington, Sacher, and Manning introduced GLO-V, a method that builds upon the distributional hypothesis, but with a different approach. Instead of relying solely on local context, GLO-V uses global word-word co-occurrence statistics to train its word vectors. This means that GLO-V considers how often words appear together across the entire corpus, rather than just in the immediate vicinity. While Word2Vec focuses on local context, GLO-V captures broader patterns, offering a complementary perspective on how meaning is constructed. As the field advanced, the limitations of models that rely on static word representations became apparent. The meaning of a word is not fixed. It changes depending on its context. This realization led to the development of models like BERT, introduced by Devlin et al. In 2018. BERT, which stands for bidirectional encoder representations from transformers, takes a step further by learning deep bidirectional contextual representations. Unlike its predecessors, BERT considers both the left and right context of a word simultaneously, allowing it to capture more nuanced and context-sensitive meanings. This bidirectional training enables BERT to understand the meaning of a word in relation to the entire sentence, rather than just its immediate surroundings. Building on these innovations, Sentence-BERT, developed by Reimers and Gurevich in 2019, extends the idea of contextual representations to entire sentences. By using Siamese or triplet networks, Sentence-BERT creates sentence embeddings that can be compared using cosine similarity. This allows for tasks such as sentence similarity, semantic similarity, and even reasoning over entire texts. These models, while powerful, are not the only methods available. The field continues to evolve, with new architectures and approaches emerging to refine and expand the ways in which meaning is derived from language. In the observatory, where the stars are distant but the connections are clear, the journey of understanding meaning through language continues. Each method, word-to-vec, GLO-V, BERT, Sentence-BERT, offers a different path, a different way of seeing the relationships that shape language. And in the quiet hum of the machine, meaning is not just found in words, but in the paths they trace and the neighbors they surround. Chapter 3: A Global Map of Co-Occurrence. In the quiet hum of an observatory, where the glow of distant stars is barely perceptible, the patterns of co-occurrence emerge like constellations in the data. Just as the night sky is a map of celestial motion, so too is the linguistic world a vast expanse of word-word interactions, each carrying the weight of meaning and context. To navigate this terrain, one must first understand the count matrices that lay the groundwork for modern word representation. These matrices, dense with numerical records of how often two words appear together in a corpus, serve as the foundation upon which many algorithms build their understanding of language. In the early days of distributional semantics, the focus was on capturing these co-occurrence patterns through matrices that encoded the frequency of word pairs. A common word like cat might appear frequently with dog and meow, while a rare word like sapphire might co-occur only with a few others. These matrices, though rich in information, were also computationally intensive and difficult to scale. The distinction between rare and common co-occurrence became a critical point of analysis. Common co-occurrences often reflected syntactic and semantic regularities, while rare ones hinted at more nuanced or context-specific relationships. It was in this landscape that Mikolov et al. 2013 introduced a breakthrough with their efficient continuous bag of words, CBOW, and skipgram architectures. These models transformed the dense matrices of co-occurrence into continuous vector spaces, where each word was represented as a point in a high-dimensional space. The skipgram model, in particular, captured the essence of word meaning by predicting surrounding words from a given word, effectively learning the semantic relationships embedded within the text. This approach, though rooted in local prediction, marked a significant shift from purely statistical co-occurrence modeling. The global approach, however, found its own voice in the work of Pennington, Sacher, and Manning, 2014, who introduced GLO-V, a method that leveraged global word-word co-occurrence statistics. Unlike the local prediction models of CBOW and skipgram, GLO-V constructed word vectors by factorizing a matrix of word co-occurrence counts. This global perspective allowed for a more nuanced representation of words, capturing both frequent and infrequent associations with a balance of statistical and semantic insight. The result was a set of vectors that were not only efficient to compute, but also rich in the relationships that defined language. Yet, even as these models refined the landscape of word representation, the distinction between local prediction and global statistics remained a key point of divergence. While models like BERT, Devlin et al., 2018, took a step further by learning deep bidirectional contextual representations, they did so by incorporating both left and right context in their training. BERT's architecture, rooted in the transformer model, allowed for a more dynamic and context-sensitive understanding of words, moving beyond the static vectors of earlier methods. This bidirectional approach, while powerful, was still grounded in the broader statistical patterns of language. Building on this, Sentence-BERT, Reimers and Gurevich, 2019, extended the idea of contextual representation to entire sentences, using Siamese or triplet structures to create embeddings that could be compared using cosine similarity. This method transformed the way sentences were understood, not as isolated strings of words but as coherent units of meaning. The influence of these methods, while significant, did not render earlier techniques obsolete. Instead, they formed a continuum of approaches, each addressing different aspects of language with varying degrees of context and statistical depth. As the night deepens, the points of these models flicker like distant stars, each carrying its own weight of meaning and context. They are not the only stars in the sky, but they illuminate the vast expanse of linguistic understanding. The work of these researchers, whether rooted in local prediction, global statistics, or bidirectional context, continues to shape the way we interpret and represent language. In the quiet of the observatory, one can see how these methods, though distinct, together form a map of co-occurrence, a map that guides the exploration of meaning in the ever-expanding universe of text. Chapter 4: Geometry Without a Dictionary. In the dim observatory, where points drift along unseen paths and the air hums with the quiet pulse of computation, the geometry of meaning unfolds in a way that defies the vocabulary of language. Here, words are not mere symbols but vectors, points in a space where distance and direction hold the keys to understanding. The dot product, a fundamental operation in this geometric landscape, measures the alignment between two vectors. When two vectors point in similar directions, their dot product is high, suggesting a close relationship. Conversely, if they diverge, the product drops, signaling a lack of connection. This is not merely arithmetic. It is a language of angles and proximity, a way of quantifying how much one idea resonates with another. Cosine similarity, a refinement of this idea, normalizes the vectors so that their length does not distort the measure. It focuses solely on the angle between them, stripping away the influence of magnitude. Two words that are semantically similar, like dog and cat, will have a high cosine similarity, even if they appear in different contexts or with different frequencies. This measure becomes the compass by which meaning is navigated, a subtle guide through the vast, uncharted territory of language. Yet in this space of vectors, directions are not fixed. Words do not sit in static positions. They shift and cluster, forming dense groups of meaning. A cluster of vectors representing sports might include soccer, basketball, and tennis. each pointing in slightly different directions but all lying within the same general region. These clusters are not arbitrary. They emerge from the data, shaped by the co-occurrence of words and the patterns of human language. The geometry of meaning is not a rigid structure but a fluid field, where clusters form and dissolve, and where the relationships between words are as dynamic as the sentences that contain them. Analogies, too, find their place in this geometric world. The classic example, man is to woman as king is to queen, is not a metaphor but a calculation. The vector for man minus that of woman yields a direction that, when added to king, points toward queen. This is not literal reasoning. It is vector arithmetic, a kind of algebra that operates in the abstract space of meaning. It reveals the structure of relationships, not their exactness, and it is here that the power of distributional semantics becomes evident. But the dimensions in which these vectors live are not literal. They are not the physical world or the world of senses, but a space of abstract features, some known, some unknown. Words like apple and orange may share a cluster, but the dimensions that distinguish them are not the ones we can name. They are distributed, spread across a space where each dimension captures a subtle aspect of meaning, and where the interplay between them gives rise to the richness of language. The journey through this space has been shaped by many hands. Mikolov et al. In 2013 introduced the continuous bag of words, CBOW, and skip-gram models, which first demonstrated that words could be represented as vectors in a high-dimensional space. These models, trained on the local context of words, revealed the latent structure of language in a way that was both efficient and effective. Pennington, Sacher, and Manning followed in 2014 with GLOW-V, which took a broader view, using global word-word co-occurrence statistics to build vectors that reflected both local and global patterns. BERT, developed by Devlin et al. In 2018, took yet another step forward, learning deep, bidirectional contextual representations that captured the meaning of words in their surrounding sentences. And in 2019, Reimers and Gurevich introduced Sentence-BERT, which extended this idea to entire sentences, using Siamese or triplet structures to compute embeddings that could be compared using cosine similarity. Each of these methods has contributed to the evolving landscape of meaning, but none is the final word. The geometry of language remains a field of exploration, where new models continue to refine and expand the possibilities of vector-based understanding. In the observatory, the points move, the paths shift, and the space itself is both map and mystery. Chapter 5. One word, several contexts. In the quiet of the observatory, where the night stretches long and the stars burn steady, the mind traces the paths of meaning, mapping the way words move through the vastness of language. Each word, a point in an endless constellation, carries with it the weight of countless contexts, shaping and reshaping its significance. One such word, bank, serves as a quiet example of how meaning is not fixed, but fluid, how the same term can drift between the solid earth and the abstract finance, depending on the path it follows. Take bank as it lies beside a river, its meaning rooted in the physical, the natural. Here, it is a place where water meets land, where erosion and sediment shape the landscape. But the same word, when paired with loan, takes on a different form, a different function, a different life. In this context, bank becomes an institution, a place of credit and capital, where money flows like water through the veins of the economy. The word remains the same, yet its meaning shifts, shaped by the surrounding words, the sentence, the world it inhabits. This phenomenon, known as polysemy, is a fundamental aspect of language. It is not merely the presence of multiple meanings, but the way these meanings are connected, often through shared elements of form or function. The word bank is polysemous, and its meanings are not isolated but interwoven, reflecting the complex web of human experience. To understand polysemy is to recognize that meaning is not static, but dynamic, shaped by context. Modern computational methods have sought to model this dynamic nature of meaning. One of the earliest approaches was the continuous bag of words, CBOW, and skip-gram models proposed by Mikolov et al. In 2013. These models captured the statistical relationships between words, representing them as vectors in a high-dimensional space. While they provided a powerful way to encode meaning, they lacked the ability to account for context in real time, as the meaning of a word could vary depending on its surroundings. A refinement came with the introduction of GLO-V by Pennington, Sacher, and Manning in 2014. GLO-V extended the idea of word vectors by incorporating global word-word co-occurrence statistics. This approach allowed for more nuanced representations of meaning, capturing the relationships between words at a broader scale. Yet, even with these advancements, the models still treated words as static entities, unable to fully grasp the contextual shifts that define polysemy. The breakthrough came with BERT, introduced by Devlin et al. In 2018. BERT revolutionized the field by learning deep bidirectional contextual representations, allowing words to be understood in the context of both their left and right neighbors. This bidirectional context enabled the model to grasp the subtle variations in meaning that arise from the surrounding words, offering a more accurate and flexible representation of language. BERT's masked language pre-training technique, where a portion of the input is masked and the model must predict the missing words, further enhanced its ability to capture the nuances of context. Building on this foundation, Sentence-BERT, developed by Reimers and Gurevich in 2019, extended the concept to entire sentences. By using Siamese or triplet structures, Sentence-BERT created embeddings for sentences that could be compared using cosine similarity. This approach allowed for the comparison of meaning across sentences, capturing the essence of what was being conveyed rather than just the individual words. These methods, while influential, are not the only current approaches to modeling language. They represent important milestones in the journey to understand and replicate the complexity of human language. Each model, in its own way, contributes to the ongoing exploration of how words move through the vast and shifting terrain of meaning. In the observatory, the stars continue their silent dance, each one a point in the sky, each one connected by the paths of light. So too do words move through language, shaped by context, guided by meaning, and bound by the ever-changing currents of thought. Chapter 6. From Sentences to Points. In the dim observatory, where the hum of distant servers blends with the quiet of the night, the transformation from sentences to points unfolds like a slow, deliberate motion across the cosmos. Each word, once a fragment of meaning, now becomes a coordinate in a vast, unseen space. The path from language to representation is not a straight line, but a series of subtle shifts, where meaning is distilled into vectors, and similarity is measured not by words, but by distance. Pooling, in this quiet world, is the act of condensing a sequence of words into a single, compact form. It is the quiet hand that gathers the scattered elements of a sentence and binds them into a singular point. This process, whether through averaging, summing, or more sophisticated mechanisms, allows the model to abstract the essence of a sentence into a form that can be compared with others. It is a necessary step, for in the vastness of language, individual words are not enough to capture the meaning of a whole. Sentence embeddings, then, are the result of this pooling, the final point where the sentence's meaning is represented as a vector in a high-dimensional space. These embeddings are not merely summaries, but distilled representations that retain the nuances of the original text. They are the coordinates that allow us to navigate the sea of language, to find those sentences that are closest in meaning, even if they are not identical in form. Semantic similarity, the measure that ties these points together, is the quiet force that binds meaning across time and space. It is the silent agreement between two sentences that they share a common path, even if their words are different. This is where the work of Mikolov et al. In 2013 becomes relevant. Their development of efficient CBOW and skip-gram architectures that laid the foundation for continuous word vectors. These methods, though focused on words, opened the door to the possibility of representing meaning in a way that could be compared and contrasted. Pennington, Sacher, and Manning followed with GLO-V, a method that used global word-word co-occurrence statistics to create vectors that captured both local and global patterns. Their work ensured that words were not only represented in isolation, but in the context of the entire language. These early methods, though foundational, were limited in their ability to capture the full complexity of meaning, especially when dealing with entire sentences rather than single words. BERT, introduced by Devlin et al. In 2018, marked a significant leap forward. It learned deep bidirectional contextual representations, allowing each word to be understood in the context of both its left and right neighbors. This was a turning point, for it enabled the model to grasp the meaning of a sentence not as a collection of words, but as a coherent whole. BERT's success demonstrated that context was not just important, but essential for capturing the true meaning of language. Sentence-BERT, developed by Reimers and Gurevich in 2019, took this a step further. It introduced Siamese and triplet structures to create sentence embeddings that could be compared with cosine similarity. The Siamese architecture mirrored the structure of sentence pairs, training the model to recognize the similarity between two sentences by comparing their embeddings. The triplet structure, meanwhile, allowed the model to learn not just similarity, but also relative distance, ensuring that the embeddings were not only close, but also ordered in a meaningful way. These methods, while influential, are not the only current approaches. The field continues to evolve, with new architectures and techniques emerging to refine the process of representing meaning. But the core idea remains the same: to transform language into points in a space where similarity can be measured, where meaning can be found, and where the path from sentence to point is both precise and profound. In this quiet observatory, the work continues, each sentence transformed, each point placed, each path drawn. The future of language understanding is not in the words themselves, but in the spaces between them, in the distances that define meaning, and in the silent, steady motion of the points that represent them. Chapter 7. Searching a Vector Library. The observatory hums with the quiet rhythm of data, its vast chambers filled with points of light, each one a vector, each one a path through the unseen. In this dim space, where the air is still and the silence is thick, the search for meaning unfolds not through words, but through the geometry of meaning itself. The vectors, arranged in a library of thought, are not mere symbols but coordinates in a space where similarity is measured not by distance, but by the angle between them. This is the domain of query embeddings, where a question is transformed into a vector that mirrors the structure of the knowledge it seeks. To search this library, one must first understand how the vectors are arranged. The process begins with the embedding of a query, a transformation that maps the question into a high-dimensional space where each dimension represents a latent feature of language. This is not a simple mapping. It is a learned representation, crafted through the training of neural networks. Mikolov et al. In 2013 introduced the concept of continuous word vectors through the CBOW and skip-gram models, which laid the foundation for understanding words as points in a semantic space. These models, though foundational, were not the only path forward. Pennington, Sacher, and Manning refined this idea with GLO-V, which leveraged global word-word co-occurrence statistics to produce embeddings that captured both local and global context. The evolution continued with BERT, a model that learned deep bidirectional contextual representations, allowing for a more nuanced understanding of language by considering both left and right context in a sentence. These methods, though influential, are not the final word. Each is a step in a broader journey of representation and meaning. Once the query is embedded, the next step is to find the most relevant vectors within the library. This is where nearest neighbor search comes into play. The search is not for exact matches, but for vectors that are closest in meaning. Cosine similarity and dot product ranking are two common methods used to determine this proximity. Cosine similarity, in particular, measures the angle between vectors, and in doing so, captures the direction of meaning rather than its magnitude. This is crucial because, in the space of embeddings, the direction often carries more weight than the scale. While dot product ranking is also widely used, it tends to favor vectors with higher magnitudes, which can introduce bias. The choice between the two is not a matter of right or wrong, but of context and application. To make the search more efficient, especially when dealing with large libraries, approximate search methods are employed. These methods trade off precision for speed, allowing for the retrieval of the most relevant vectors without the computational cost of an exact search. Techniques such as locality-sensitive hashing or tree-based structures enable this approximation, ensuring that the search remains practical even as the library grows. The library itself is not a static collection, but a dynamic structure, shaped by the data it contains and the queries that seek it. Retrieval augmentation further enhances the search process by incorporating additional information beyond the raw vectors. Metadata filters, for example, allow the system to narrow down results based on attributes such as date, source, or category. This is particularly useful in domains where the context of the information is as important as its content. The library, therefore, is not just a repository of vectors, but a curated space where meaning is both preserved and refined. Yet in this space of vectors and similarity, a distinction must be made between relevance and truth. A vector may be highly relevant to a query, yet the information it represents may not be accurate. The library, for all its power, is a reflection of the data it has been trained on, and its contents are shaped by the patterns it has learned. Truth, in this context, is not a measure of similarity but of correctness, of alignment with reality. The search for relevance is a necessary step, but the pursuit of truth requires a deeper engagement with the data and the world it represents. In the observatory, where the points of light drift and the paths of meaning unfold, the search continues. It is a quiet, precise act, guided by the geometry of language and the interplay of similarity and truth. The library remains vast, but the path forward is clear. Chapter 8: What the Space Inherits. In the quiet of the observatory, where the air hums with the faint resonance of distant stars, the patterns of meaning are traced not by light but by data. Words, like celestial bodies, are positioned not by their intrinsic weight, but by the paths they follow through the vastness of language. To understand how these patterns emerge, one must consider the subtle forces that shape them, forces that are not of the cosmos, but of the minds that have shaped language over centuries. The process begins with the training corpus, a collection of texts that serve as the foundation for learning. This corpus, though seemingly neutral, carries the fingerprints of its origins. Training corpus bias, for instance, reflects how the perspectives, values, and even the languages of the texts influence the model's understanding. A model trained on texts from a specific region may not grasp the nuances of another, just as a star's light may be distorted by the gravitational pull of nearby objects. Frequency, too, plays a role. Words that appear more often are more likely to be positioned closer to one another in the model's space. This is not merely a matter of repetition, but of pattern. How often two words appear together shapes their relationship. Cultural associations further complicate this picture. A word may carry different meanings in different contexts, and these meanings are not always captured by frequency alone. A model must learn to distinguish between the cultural weight of a term and its literal use. The challenge of multilingual alignment arises when models must bridge the gap between languages. A word in one language may not have a direct equivalent in another, and the task of aligning these meanings is as intricate as mapping the constellations of different skies. Models must learn to recognize the commonalities and differences, much like an astronomer must reconcile the apparent positions of stars with their true locations. Domain shift introduces another layer of complexity. A model trained on one type of text, say, news articles, may struggle when applied to another, such as legal documents. The structure, vocabulary, and even the intent of the text differ, and the model must adapt, much as a telescope must adjust its focus to observe different celestial bodies. Anisotropy and hubness, meanwhile, describe the uneven distribution of points in the model's space. Some words, like central stars, appear frequently and are connected to many others, while others, like distant planets, are fewer in number and less connected. This unevenness can affect how the model generalizes and how it handles rare or ambiguous words. Evaluation, in all this, is not a mere afterthought but a critical act of observation. Just as an astronomer must calibrate their instruments to ensure the accuracy of their measurements, so too must a model be tested against a variety of tasks and data sets. Evaluation reveals not only the strengths of a model, but also its limitations, guiding the refinement of its structure and the expansion of its training. The methods that have shaped this landscape are as varied as the stars themselves. Mikolov et al. In 2013 introduced the CBOW and skip-gram architectures, which laid the groundwork for creating continuous word vectors. These models captured the essence of words through their surrounding context, much like a star's light reveals its composition. Pennington, Sacher, and Manning then introduced GLO-V, which took a different approach by using global word-word co-occurrence statistics, offering a more holistic view of language. BERT, developed by Devlin et al. In 2018, took a step further by learning deep bidirectional contextual representations. It looked both to the left and the right of a word, capturing the full breadth of its meaning in the flow of text. Sentence-BERT, introduced by Reimers and Gurevich in 2019, built upon this by using Siamese or triplet structures to create sentence embeddings, comparing them through cosine similarity. These models, while influential, are not the only tools in the astronomer's toolkit, nor are they the final answers to the questions they seek to answer. In the observatory, the patterns continue to evolve, shaped by the data that feeds them and the methods that refine them. Each model, like each star, has its own place in the sky of language, and the act of observation remains essential to understanding where it stands. Chapter 9. Are numbers meaning? The observatory remains quiet, its glass dome closed against the night. Inside, the air is still, carrying the faint hum of distant systems and the weight of accumulated knowledge. Points of data drift across the walls, not in patterns of meaning, but in paths of calculation. They do not speak, do not gesture, do not seek to be understood. They are merely the residue of thought, the trace of effort to make sense of the world through numbers. And yet, in their arrangement, in the way they cluster and diverge, there is something that feels almost like intention. The history of language modeling is a quiet accumulation of these points, each one a fragment of meaning, each one a step towards something more complex. Mikolov et al. In 2013 proposed that meaning could be captured through vectors, continuous representations of words that could be added, subtracted, and compared. Their models, CBOW and skip-gram, introduced a way to represent words not as isolated symbols, but as points in a high-dimensional space. These vectors did not yet carry the full weight of context, but they were the first to suggest that meaning could be distilled into numbers, and that those numbers could be used to predict the next word in a sequence. A few years later, Pennington, Sacher, and Manning built upon this idea with GLO-V, which took a different approach. Instead of training a neural network to predict surrounding words, GLO-V used global word-word co-occurrence statistics. It treated meaning as a matter of frequency, of how often words appear together. The result was a vector space where words were not only placed based on their neighbors, but also on their broader relationships. The vectors were not as dynamic as those from neural networks, but they carried a kind of stability, a sense of the world as it had been recorded across vast corpora. Then came BERT, a model that changed the game. Introduced by Devlin et al. In 2002, it did not treat words as fixed points, but as elements within a flowing stream of meaning. BERT learned to understand words in the context of their neighbors, both to the left and to the right. It was a model that could look ahead and behind, that could grasp the nuance of a word based on the entire sentence it was part of. This was a significant shift, one that moved language modeling from static representations to something more fluid, more alive. But even BERT was not the final word. In 2019, Reimers and Gurevich introduced Sentence-BERT, which took the idea of contextual representation and extended it to entire sentences. Using Siamese or triplet networks, Sentence-BERT created embeddings for sentences that could be compared using cosine similarity. This allowed for a new kind of comparison, one that was not just about individual words, but about the structure and meaning of entire phrases. The model did not seek to understand the meaning of a sentence in the way a human might, but it could tell when two sentences were similar or different, in a way that felt almost intuitive. Each of these models, in their own way, sought to bridge the gap between the abstract and the concrete. They did not invent meaning, but they provided a way to represent it through numbers. And in doing so, they created a space where meaning could be measured, compared, and even manipulated. Yet, none of them claimed to capture the full breadth of human understanding. They were tools, not minds. They were systems that could approximate meaning, but they could not replace it. The observatory continues its quiet work. Points of data move in their own rhythm, paths form and dissolve. There is no grand design, no singular purpose. Only the steady accumulation of knowledge, the quiet persistence of numbers that have been given form. And in that form, there is a kind of order, a kind of clarity. Not meaning, but the possibility of meaning. Not understanding, but the shape of understanding.